All right, it's recording. So this is a typical statics problem that you could see on a test. I wrote the problem. I did make the pin and the roller kind of shown as the initial problem, and then the FBD will show the reactions. Okay, so the things you need to make sure of is we're going to keep a positive x and positive y coordinate system. Then you need to note that you have 3 equations of static equilibrium at your disposal for any of these problems. Starting on Wednesday, this problem is going to be, once you solve for the external reactions, we're going to solve for, remember, AB, AD, BD, CD, and CBC. We're going to solve for the internal forces, which means that we will determine whether or not each one's in tension or compression using the same equations. But you must first get these successfully. If you don't understand this, you're not going to understand Wednesday and Friday. Okay, and then we build them. So once you get all this, there is a point we're going to actually build trusses, test them, and have a competition. Okay, so with that said, the first step, what you have to do. Okay, step 1, take the truss and make an FBD. Daily, what's an FBD? Really close. Myers? Free body diagram. Free body diagram, okay? So we have to take this truss and rewrite it, but I'm going to go C left. I'm just going to replace. In this case, it's going to look exactly like that, but just replace the pin and the roller with external reaction supports. That would be AY and AX, and this would be CY, and that's it. That's a roller. It does not restrict motion in the X direction because it's a roller. We want it to be able to move. Question so far, how to get the FBD. So this is technically your FBD. All I did was replace the hinge, keep the loads on there, put the distances, everything's there for you, and we're moving on to step 2. Is calculate the external reactions. Now, why are they external reactions? Why are these external reactions?
Because they take place on the outside of the outlet.
Outside of the truss, exactly. They're acting on the outside of the of the truss. These members have internal forces. Okay, so like when you pull, I get a piece of a balsa wood over here, and we get Elijah here, and we pull on this. Let's just pull it with a tensile force. Where's the force? Elijah and I are pulling with the same force, right? Both in tension. But wouldn't you say there is a force in there and it's going to break eventually, right? Let's break it. Oh, broke there. Grab it with 2 hands. Try to pull it right from the middle, see where it breaks. Only a tensile load. It's almost like a cable. Yeah, it broke again. That's all right. There was a force there which it broke. So, indeed, it was a tensile force. Now, if we make this a compressive force, okay, and we push, it buckles really, really far before it actually breaks. So, it's just breaking in the middle. It's buckling. It's called lateral buckling. Okay? Those are internal forces. External, internal, you're going to be able to calculate both of them eventually. So, first thing, in order to figure out what the internals, we need to know what's acting on the outside. That's why we do that. All right, so first one. Some of the forces in the X. What forces are acting in the X direction? Only in the X direction.
400-pound load.
And
AX.
right? Praska, is he right?
Yeah. All right.
So I have AX, positive. What direction is 400?
Negative.
Negative. It's going to the left, equal to 0. Okay? Can I solve for AX?
Yes.
All right, good. AX is equal to 400 pounds. Box your answer. It looks nice. Keep it like that. What?
Bicycle like this truck.
See, look, you remember that. I'm serious about that. It's true. The more neat you are with your problems in college, the more points you're going to get on problems. Usually, it's not even the professor who grades your stuff. By the way, you have TAs and grad assistants. Depends on the school. Next equation. Sum of the forces in the Y. Hawthorne. Pick on you.
AY and C.
AY and
C.
CY and
1,000.
1,000, right? Is acting in the positive or negative Y.
1,000 going negative.
All right. AY plus CY minus 1,000 equal to 0. We have how many unknowns? 2. What are?
It's AY and CY.
AY and CY. Can't solve them right now. Cannot use one equation and 2 unknowns. We need something else, and that's where the moment comes in. I think you guys, everybody good so far with your, like you got that far correct? And here's where all the mistakes came with the last section. What point did you guys use to take the moment about?
C.
You use C? C? A? Seamus? Does it matter? Doesn't matter. Last class I used A. You could even use D, but it's going to get even more. Now you have 2 equations and 2 unknowns. We want to pick a point, remember, strategically, so the distance that the moment is going to be 0. So pick A or D to eliminate any of these forces, either CY or AY. So I haven't done it with, we'll do it with C. The moment about C and counterclockwise is positive. Okay? That means CY is, what's the distance for CY? 0. There's no perpendicular distance, so that's 0. That will eventually go to 0. I'm going to use the 400, and it's counterclockwise around C. So it's going counterclockwise, it's positive, plus 400 times 10. Now I got 1,000 going around C times 16 feet is the perpendicular distance. Now I'm going to do a negative AY times 26 feet equal to 0. Now I didn't write AX there. AX is on the same plane. Okay? It's on the same exact plane. It would go through C. It would also be 0. You with me? Look at check. So you got this big long equation. This goes to 0. CY goes to 0. What are you left with? You're left with 4,000 plus 16,000. Take that over, divided by 26. Do the math. You get AY is, what is 16 plus 4 is 20,000, which would be negative. Or take the positive. Well, it doesn't matter how you do it. If you want to take AY 26 times 26 over to that side to make it positive, and then divide it out, you're basically going to get 20,000 over 26, which is equal to, somebody calculate that for me?
769.23.
769 point what?
23.
Pounds is equal to AY. Okay? Box your answer. Robertson. What now?
You plug AY back into the...
Yep. Take your AY, bring it all the way over to here, and plug it back in. And we get that 769.23 plus CYs are unknown, minus 1,000 equal to 0. So CY is equal to...
Which class? Wouldn't 769 be negative? It's AY.
No, I brought 26AY over to the right, which made it positive,
Okay.
and kept those over there on the left.
Okay. Oh, okay.
Okay? Yeah, I kept... See, I could have took these over, made them negative, and then took the negative 26 over, and that would have made it positive anyway.
Yeah.
But we know AY has to be positive. Because you got 1,000 pulling down, these two added together better be 1,000. Okay, so what is CY? 1,000 minus 769, which is 2. Somebody?
31.
231 pounds. Box your answer. And you have successfully solved for the external reactions. That's it.
Is it okay if we circle them?
Huh? Yeah. Bass.
I got like really close to that, but like they're off by like
A couple what?
a couple numbers.
Like, are we talking decimals or are we talking whole numbers?
Well, yeah, like a whole. Like when I did, because I did it from the A,
From the A?
but at the moment I got C.
I'd have to see, but you're probably correct.
Right.
Anyone else get it fully correct? Good. That's it? It's alright if you didn't. You did? Alright. So there's your example. Now, starting on Wednesday, this is an easy trust to start, but we're going to get the internal forces and use something called the method of joints to figure it out. So write this down real quick while I'm going to write up another little problem here before we move on. Yes, I'm giving you another example. Because we've only done trusses, some students have not really did an easy beam. There was a beam, a simply supported beam example in one of your PowerPoints. I want to make sure you understand that static equilibrium equations can be used to solve beams, trusses, frames, members, all sorts of things. And then eventually get shear and moment diagrams. Are you guys still... Can I erase that? This? All right. There is our simply supported beam, and there's a reason it's simply supported. The first type of beam you'll analyze in statics, everybody that takes statics in college, is meaning that it doesn't matter how many loads I put on there, simply supported means what are the supports here? You got a pin and a roller again, okay? And we're going to learn about determinacy on Wednesday, static determinacy. If I would put a roller there, okay, there is a way to figure out if I can determine something unstable even before I analyze it. So you would all say, if I put a roller there, do you want to drive your car over that bridge? If I put two rollers instead of a pin, what's going to happen? It's going to go left and right, and eventually somebody's going to crash. It needs to be stable and determinate is the engineering term. The minute this becomes a roller, it's no longer statically determinate, it's statically unstable. Okay, and there's a little formula we use, 2j equals m plus 3, to figure out if something is determinate or not. So if I gave you a truss, and I am going to make it simply supported, would you guys drive your car over that truss?
No.
That's what it needs. Does it need this? Not necessarily. In theory, this is all it needs. One diagonal member to make it stable. The minute you take away a member, and I'll show you this on Wednesday, I don't think that is stable. That is also unstable. Yeah, you need to make sure that your trusses are stable before you analyze them.
Wait, so you're driving on the bottom, right?
That's a normal, like, think about the free bridge.
Yeah,
Right.
right. I was just making sure. I was just making sure you're not like driving up on top.
The free bridge has a big hinge. Nope. Looks like that, right?
Yeah.
With vertical members, maybe even two more. I don't know what it looks like, but something like that. And you drive right there, there's a roadway.
Yeah, I was just making sure. You know.
It doesn't really matter. If you're looking at your 33 bridge, the highest bridge in PA on the east coast, on the east side of PA, you have a huge steel deck truss system that is connected to big piers. And here's the Lehigh River way, and I was around. There's my water, and way underground is the biggest footer I've ever seen to support. I mean, you're looking at 180 feet, is it? 120? You know where I'm talking about over here, right? 33 bridge? 33 going to 78.
Yes.
You're down by the boat ramp, and you look up, and there's that huge bridge. That's the bridge I'm talking about.
Is that where the catwalk is?
Yes, there's a there is a huge catwalk because they had to get to it. But what they do is excavate around and get this huge footer. I mean, on bedrock, you're talking, the river's dry. So when they do a cofferdam, like they actually dam up the river, put barriers and pumps, and they pump out the water constantly 24 hours to make sure that they can build the footer that this pier is supporting the truss above. And there's like 2 or 3 of them, I think. It's a long, high bridge in one of the records. So the truss doesn't necessarily have to be above, is what I was trying to get at, all right? So let's do our simply supported beam, then you're going to do those other trusses. Here's our beam. We have 2 loads now that are acting at 3 feet from the left and the 200-pound load 3 feet from the right. I wanted to put something that's not exactly in the middle because we've been doing this the whole time so the numbers will work out. Let's create our FBD, step 1. FBD. Daly, what's that stand for?
Free body diagram.
Very good, Daly. Okay, here's your beam. I'm going to make my reactions. We have AY. Here's point A. Here's point B. AX. And that's B today. BY. And I'm going to put my loads, I should have colored them differently. I'll put them in blue now. 150 pounds and 200 pounds. And that's 3 feet, 4 feet in the middle, and 3 feet. Okay? That's my FBD. Hawthorne. What's AX going to be?
You don't know that yet, right?
What do you think it's going to be?
0.
Why, Jameson?
There's no other forces.
There's no other forces in the X. Okay? I want you guys writing this down. You don't have a simply supported beam in your at all. So next thing, step 2 is to calculate the external reactions. How do you do that? Let's verify Jameson's claim. So Jameson, there's nothing acting in the X other than AX. So AX is equal to 0. Now, some of the forces in the Y. AY plus BY minus 150 minus 200 equal to 0. Okay? Cody, you alright with that?
Yeah.
Okay? So now I have the sum of the moments about a point. Again, pick a point. Do I care which one it's going to be, Max?
No.
Don't pick an internal point. You want to pick something, A or B.
Yeah.
Let's pick A this time, Max.
Alright.
Sound good with you? Counterclockwise is positive?
Yeah.
Alright, so we have AY times 0 plus AX times 0. There's no distance. Now I have 150 minus 150 times 3 feet minus 200 times 7 feet plus BY, and all our variables are colored this time. BY times the total distance is 10 feet equal to 0. How many unknowns in that problem? This goes to 0, this goes to 0, and that's what we're left with. We have 10 BY. I'm going to rewrite it, bring these two to the other side. So what is 450 plus 1400 is 1850. So BY is equal to 185 pounds. So we just solved for BY. That's 185. Now take the BY and pull it back into this equation. And what do we get? AY plus 185 minus, 150 minus 200 equal to 0, leaving us with AY is equal to 350. 351 is 185 pounds. So AY is 165. Does that, common sense wise, make sense to you guys that that should be lower than that?
Yeah.
Can you guys see that? Engineering wise, Frasca, why would AY be less than 185 with the reaction here? It's
There's less force on that side.
there's less force on the left side. That's a greater magnitude, obviously only by 50 pounds, but it does change our external reactions. So if your numbers come out that that would be more, you better think in your head like, hey, I messed something up. I need to change it. I need to go back and fix the sign or whatever. But here's a perfectly good test problem on how to solve external reactions from a beam and not a truss. Okay? So you have 3 trusses I gave you on the back of that. Okay? 3 trusses I gave you. I do. Here. Here's how it's going to go. Row 1. You're teaching the class. Row 1. You each individually do it. Get together after 10 minutes. See who's right, see who's wrong. I'm not going to tell you. You better get it right. This row 1. This is row 2, number 2. And this is row 3, number 3. Okay? Now, you need to, it's hard for you to see. I probably want to draw them because the copier didn't come out. I'm going to draw them for you. Number 1, because you can't see the grids, I'm giving you. Each grid is 1 foot, but I'll give it to you anyway. So, each individually you're going to do it and then get together. Make sure you guys, this is number 1. Here's the roller on this side.
Oh, they're changing it up on it.
They are. That's 20 pounds. 10 pounds. 100 pounds. So the distance is 3 feet from here to here. 3 feet from here to here. 2 feet from here to here. 1 foot, and that's all you need. You don't care about the angles. That's the tip I'm going to give you guys. You don't need to worry about the angles right now. You're calculating the external reactions. Number 2. Row 2, this group. You're only worried about yours. The class, you're going to teach the rest. Do it much neater in your engineering notebooks, please. All right, this is 4 feet, number 2. This is 2 feet horizontally, and this is 3 feet vertically. And if you wanted to know this, that's going to be 2 feet. That's all you need to know. Number 3. Three feet, 2 feet, 3 feet, and the vertical distance is 2 feet. For number 3, the tips. All you care about are perpendicular distances. That's why angles don't come into play. All forces that I wrote here are always in the X or Y direction. That's why it doesn't matter. So, again, row 1, each individually do it, calculate the external reactions, get together. Somebody better be right, you're teaching. 2 and 3 right here, this group. You guys, and number 3, you're that one. Yes? Yes?
So would that be positive instead of negative?
Always keep, good question, always keep your, as long as you keep your coordinate axis like that, everything will make sense. So if they're pointing away, does that tell you that's a positive 20?
It's a negative 20.
It's a negative 20. Always go back to this, and then you'll be safe, okay?
So like, when we're doing this from this point, we can still put AX this way, and then
Yes.
Y this way.
Yep. I use common sense there too, but
Yeah.
because there's 20 pulling that way, I'm going to put the reaction that way. It only makes sense.
Yeah.
But always just keep your signs according to the positive X, positive Y.